good. I've had a few people come to office hours. That always gives me kind of a sense of how things are going in some small amounts. Because I interact with a few people. Yeah, I've had a few people. There's lots of room in my office. If you're having challenges, come visit me. There is room in my office. Lots of room. I've generally been averaging like 2, maybe 3 people at a time, but I can easily fit up to like 6, 7 people. So anyway, all I'd say, there's room. If you are struggling, if there's question, like whatever it might be, if you're having difficulties, come visit me. I will happily work with. All I do is I just ping around my room. My room is there's basically a table in the center with chairs around it, and then I just kind of ping around it and help people at various places. So it's not. I don't have a traditional office where like my chair is here and there's a desk here and I can fit 2 people in front of the desk and that's it. No, it's a table with a bunch of whiteboards on it, and I have a giant whiteboard on the wall, and I just ping around and I work with people the entire time. So. Come visit me, or don't, up to you, but I just always remind you all that exists. The last quiz was just last Saturday, 1D kinematics quiz. Normally would be due this Saturday, but because we're only finishing it today, I sent out an announcement, told you all that the quiz for 1D kinematics, quiz 2, 1D kinematics is due. I gave a slight extension on it, so it's due the 29th because it takes us a little bit. So there you go. We're going to easily finish 2D kinematics this week. Maybe like, how are we going to have enough time? 2D kinematics is just a extension of 1D kinematics. It's doing 1D kinematics twice. Like getting through the content won't take me that long. We'll be able to spend most of the time, hopefully on Thursday, at least half of it, if not more, just doing 2D kinematics problems. So, and then we'll do forces, and that'll be the test that we have will pretty much be kinematics and forces. That's the 2 main things that'll be on it. We spend 2 weeks on kinematics. We spend 2 weeks on forces. It works out great. So there you go. I think that's it. Remember the assessment. If you want the bonus points or whatever, you got to get that done. I forget if I said it was Tuesday or Wednesday when it was due. Sent it in the announcement. I forget the exact date. It wasn't set by me, which is why I don't remember it. But if you want that extra credit for doing the pre-assessment, please do so. It's good for me as well. It gives me information, data. Okay, recap of last class. 1D kinematics, 1D motion. So last class, we went through the equations. Where are those things at? Boom. And this looks a little bit messy. I'm just going to copy and paste this for the 3rd time and delete all the things. Weird. Oh, there you go. All right. This is the equations. It looks like a lot, and it might look intimidating because you're like, oh man, all the letters. But this is actually one of the most, and I say this not, right? You're given, what's missing, find the equation that has what you have and has what you need, and then plug in the stuff. This is actually one of the most straightforward parts of the class, and I'm saying that not to tell you, if this doesn't make sense, how dare you? I say that if you just practice a few of these and you go through the motions, what's given, write it down in variable form. What are you solving for? Write it down in variable form. If you go through those motions like this, that is the skill I need you to know. And if you know this skill, you will be solid on this. That is really like every single one of these problems basically boils down to it. The last problem I did give you had one little trick to it. We talked about it. Where in this problem we said the time when their positions were equal. And so in that case, we said we could take the equation for the position for one person and set that entire equation equal to the position for another person. So just to kind of write that out, that's what it shows here. We had 2 people, Pablo and Jacob, but if we set these 2 equal to each other, it just ends up being x initial 1 plus v naught t plus 1/2 a1 t squared. There's 2 people, so they each have their own variables associated with them. This thing's so loose, I don't want it to keep falling off. Equals x naught 2 plus v naught 2t plus 1/2 a2 t squared. 2's on the right, 1's on the left because person 2 gets their own variables. Person 1 gets their own variables. And because their final position is the same, we can actually take the entire equation and set it equal to the other entire equation. That was a little trick here. It's a really good problem. Make certain you work through this one without this in front of you. That's always a strat. Do not start these problems with the worked out solution in front of you, because otherwise it's not helpful. Like, I say not helpful. It's maybe a little helpful. You are not training effectively in that case, because you should train the way the test is. Learning is best. At some point, you got to try for yourself, and then you can refer to this if you get stumped. Refer to it, figure out the next step, then put it away again. If you just follow through with this, and that is the way you study for this class, it's not going to go well in the test because you prepared the entire time with like all the information available to you. When it comes to the test, you're not going to have that. So training your brain to actually work through these without all the information, without the whole full worked out thing. Yes, it hurts your brain. Yes, it's going to make you have to try harder, but it's just how it goes. That's how learning happens. All right, so anyway, good problem. If you haven't already realized it, there's a problem like it on the quiz. Okay, so the end of class, this is the next big chunk. This segues really nicely into 2D kinematics, so it actually works out great. Gravity, something you're all very familiar with. It pulls everything down. In this class, so we're going to do a lot of problems with things in the air because we all live on Earth. It's a thing that pretty much any physics problem you ever do, gravity is going to be involved. Like gravity is going to exist. It's going to be on Earth. So it's important for us to talk about it. To that end, if something is in the, look, even if it's not in the air, it experiences gravity. Everything on Earth experiences gravity. But in our case, we're going to consider it when it's in the air. If something is in the air, and there is no other forces acting on it, no air resistance, no jet engine attached to it, no propeller, it is in the air. That could be this ball as I toss it upwards. When it's in the air, the acceleration it experiences will be negative 9.8 meters per second squared. This is how gravity pulls everything down with this acceleration. I don't care what it is. Baseball, rocket, well, rocket's got a jet. Baseball, car, boat, I don't care. If it's in the air somehow, some way, in the air, y is negative 9.8. And the reason I'm putting this y here is because gravity only pulls things down. Does not pull things left and right. So this is a little segue, like foreshadowing of when we get to 2 dimensions. If I put this baseball on this desk, gravity is not going to cause it to roll left or right. Gravity pulls things down. Now, if you're like, well, what if you tilt the desk? We'll do inclined planes eventually, and that's its own thing. But everything on these desks here, great, gravity's affecting it, but they're not sliding left to right. Gravity does not pull things left to right. Gravity only pulls things straight down. Acceleration is negative 9.8 meters per second squared. And so we're going to sit with this number for a little bit and try to make some sense of it and see what it affects. I also pointed this out over here. If you're moving, I forgot to, I guess, update this. If you're moving down, your delta y is going to be negative. I'll show you all some examples of why that is. That's not something you have to memorize, but that's just a nice, I'm mentioning it because the more I mention it, the less likely to make a mistake. If you're going downwards, your delta y is going to be negative. We'll see that very simply when we do a couple problems. Yeah, and there you go. This is a given now. Something's in the air. I'm not going to tell you that a is negative 9.8. You have to know that. That's one of those things that you just have to kind of know. There is a few things that you have to memorize in physics, like a handful of things, and that's one of them. I say that. It's actually on the formula sheet, so you don't need to really memorize it. Anyway, let me make sure and actually hit the button. Great, I did. Okay. We're going to skip this problem because it's extra kinematics practice. Feel free to try it out yourself. Here's our first real question about gravity. All right, so a wrench and a feather. And just to make this segue a little bit nice, I'll leave it as a wrench. I should have changed it to hammer. It doesn't really matter. A wrench and a feather are both dropped at the same time. Which will hit the ground first? Assume no air resistance. Very, very, very important that there's no air resistance. There's only one right answer. All right, go like 20 more seconds. All right, and yeah, sure. I will count very, very slow. 5, 4. Well, here, look, I'll even leave it open. All right, now I'm going to do something really weird where I'm going to answer this question with the YouTube video. And so that's weird because it's going to be a stream of a YouTube video. So I don't know. YouTube hasn't like taken down any of my videos for this yet. So NASA wrench and feather. It's not a wrench, but it will still work. All right. So this is a cool video because it's the Apollo mission. So they did this experiment. Let's go to somewhere without air, the moon. Now they knew the answer to this without having to go to the moon. Like they didn't need to do this to prove this. But I really like it because I don't know, it's just cool. So leave that open. Well, hopefully everyone's responded. I'll give 3, 2. Well, whatever. Actually, not minimize it. I just want it out of the way. Okay. Great. They're on the moon, and the video quality is not phenomenal because this is in the 70s. Like that's the last time we went to the moon. It's been a hot minute, y'all. If you didn't know that. Nope, wrong one. There you go. And also, it's a camera on the moon, which sounds real simple, but it turns out it's really hard to make electronics work in space for all sorts of reasons.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time.
There they go.
How about that? They'll hit the ground at the same time.
So just they both hit the ground at the same time. Now, yes, gravity on the moon is weaker than on the Earth, but that doesn't matter here. What matters is that all things are affected by gravity the same. So gravity, let me rephrase that. All things experience the same acceleration due to gravity. So the answer is, as uncomfortable as this is, the answer is the same. Again, so there's a video proving it, but I'll also show you all something that hopefully makes it feel a bit more comfortable. So I got 2 sheets of paper. This is something, it's the easiest way I found to explain it. You can do it with elementary school students or anyone. It's really nice. They're the same mass, same amount of, roughly the same amount of atoms in them. But if I just crumple one up, I haven't changed its mass. They both have the same amount of atoms in it, but you know, if you drop them both, the one that's smaller hit the ground first. What's the only thing that's different? The surface area. The air resistance is higher. So if you get rid of the air resistance, they will both fall at the same rate. But this is just to show it's not based on mass. These have the same mass. So it's a nice little easy kind of thing to show that mass is not the thing affecting it. Those are the same mass. It's based on air resistance. That's the reason things fall at different rates. Now you may be like, but I live in air. Yes, that is true. For us to actually solve problems with air resistance, it would be way more complicated. And it turns out you can get a pretty darn close right answer by ignoring air resistance. Air resistance does not affect things as much as you'd expect. It does affect things if you're going really fast or you have a really big surface area. You know, parachute, huge surface area. Or if you got like a car going 60 miles per hour down the road, that's kind of both. It's going pretty, somewhat fast, and then it's got a big surface area. But like a ball getting tossed, air resistance really, like, if I did the math for this, it would actually be quite accurate to the reality. And most things, like if you jump out of something in the beginning, air resistance is not going to affect you that much until you get going really fast. So ignoring air resistance actually lets us get a pretty good sense of what's going to happen for most things. And, you know, if you wanted to be air resistance, we got to walk before we can run. We start simple. And to be honest, air resistance is an absolute nightmare to calculate. Even engineering majors generally, unless they're like aerospace engineers, they don't have to deal with it. So I say that it's good enough for us, and let's just actually do things. Okay. This one we'll spend a bit of time on. I'll have you all, let's see, do we want to, yeah, let's just work through this one. We'll work through this one and then we'll test it. So this is going to be a classic problem with gravity, like super straightforward. And there's only one number given, and yet we can do the entire problem. A wrench starts at rest. There's my wrench. And it falls from a height of 3 meters. How long does it take to hit the ground? All right. So we write down our givens. We have our nice, beautiful picture here. Remember, we always need a reference frame. Where do you all want 0 to be? There's an infinite number of correct answers here. Pick the one that's probably the most intuitive. Where do you all want 0 position to be? The ground sounds like a great idea. Now, I'm going to use y instead of x. This is going to be something, again, this is just preparing us for 2D. When we're talking about up, down, we're going to use y. When we're talking about left, right, we're going to use x. The equations all work the same. We can use all the old equations. Everywhere the equation had an x, we can replace it with a y. But this is just how we tend to kind of denote these things. So y final is 0. And by extension, that means y initial is 3 meters. Boop, 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 boop. So y initial is 3 meters. Y final is 0 meters. And the new thing we know is that the acceleration it experiences, there's no jets attached to it. There's no rockets. There's no anything else. The only thing making it fall is gravity. And gravity makes things accelerate at negative 9.8 meters per second squared. So this is also a good opportunity, and the next problem will be related to this. All this number says is that every second, my velocity is changing by negative 9.8. So if I drop something, after 1 second, it'll travel 9.8 meters per second downwards. After 2 seconds, 9.8 times 2. After 3 seconds, 9.8 times 3. The definition of acceleration is how much does my velocity change every second. Every second it changes by that amount. You just add negative 9.8 to whatever your velocity is, and that's... So if in this problem I said, hey, how fast is it going after 1 second? It's just negative 9.8. Anyway, that's the next problem. Number 2, how long did it take to hit the ground? We're solving for time. Step 3, we're going to choose our... Oh, there's one more given we know. I'm going to let you all see if you can figure it out. I'm not going to even tell you. Spend 20 seconds. See if you can figure out the other given. Starts from rest. So what? What does that tell us? Velocity initial is 0. Now, something I want to point out here that's also going to be a common trend, its final velocity is not 0. The trap that a lot of people fall into is I'll say stuff like hit the ground, and people will be like, oh, when things hit the ground, they stop moving. Yes, that is true. When things do hit the ground, they stop moving eventually. But if you notice, even when I dropped the space ball, like it bounced a little bit. Depending on the object you drop, it might bounce, roll, shatter. That's a complicated problem. We do not do the problem of hitting the ground. We do the problem of it falling and right before it hits the ground. So anytime you all see this phrase hits the ground, basically assume right before it hits the ground. And I even in my picture tried to be really careful and put a tiny, 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 tiny little gap there to just denote that. The final velocity when you hit the ground is not 0. That would not be a very interesting problem. Just think about that. That would say that I start at rest and I end at rest. And then the question is, how the heck did I get down there? Like, you had to move. So we don't do that. Even though I say hit the ground, always assume I basically have the phrase right before I hit the ground. Like, assume that that's in there. Anyway. All right, try to find the kinematics equation, y'all. You got your givens. Remember, everywhere there's a y, you can replace with an x. Let's see. I think I have that. Oh, I had that slide. I guess. Let's see. I don't think I can fit all of them, in the same slide and still have you be able to see everything. But you know what? I'll try. So which equation are we going to use? Ugh, that doesn't really fit. Anywho, look through your stuff. See if y'all can find it. I sadly can't show both. It's just not enough space. All right, I made it work. So everywhere there's an X, we can change with a Y. That's all I'm going to do here is I'm just going to rewrite these with Y's. Well, it's going to fight me, but that's fine. Whatever, it's going there. Anywho, so they're all the same equations. You just replace X with Y. And you say, all right, what are we solving for? We're solving for time. So we can only choose an equation that has time in it. Like if you want to solve for time, we better choose an equation at some point that has time in it. So this one's got time, this one's got time, this one's got time, and the bottom one doesn't have time. Again, you can do extra. You could find the final velocity, like that's an option, and then you could do these. But just for the sake of doing it in one shot, what do we have? We have Y initial, Y final, A and V naught. This one's got all those things. And it works out nicely for us. So that's the one we're going to choose to do. If you instead said, forget that, I want to do this bottom one. You could totally do this bottom equation. You could find the final velocity. And then you could plug that into this top equation. It would totally work. Totally valid. Nothing wrong with it. But that's just an extra step. Not a bad thing. All right, so we're going to choose this one. So my Y, and I'm even going to remind you all that, remember that Y of t is the same thing as Y final. V naught t plus 1/2 at squared. Step 4, plug in the numbers. My Y final is 0. My Y initial is 3. My initial velocity is 0 times time plus 1/2 times negative 9.8 times t squared. We're spared having to do the quadratic formula because 0 times t is 0. And then remember I told you all if you're falling downwards, your delta y is negative. 0 minus 3 is negative 3. So when you kick that 3 to the other side, oh look, we get a negative, just like I promised you would. If your final location is lower, it spits out a negative when you subtract them. 0 minus 3 is negative 3. All right, so that equals negative 4.9 t squared. You will know that you forgot to put it as a negative because if you, I'll do this on a new slide and make it a little bit bigger because I want to point out a couple things. Remember, checking your stuff, double checking your work or having ways to check for mistakes is super useful because you will make mistakes. I can promise you that. It's a guarantee. So there's all the things. Move it on up there. Write this a tiny bit bigger. And now I have space so I can actually show you in case you're like, what the heck? Subtract 3. So negative 3 equals negative 4.9 t squared. If this isn't a negative, my negatives won't cancel. And if your negatives won't cancel, so let's just write t squared equals negative 3 over negative 4.9. If your negatives don't cancel, you're going to do the square root. If you do the square root of a negative number, it gives you an imaginary number, which for this class is not going to ever happen. None of your answers will be imaginary numbers. If you ever took quantum mechanics one day, you would find imaginary numbers, and they do mean something. So in physics, the square root of a negative number actually has a physical significance associated with it, but not in this class. That's just fun facts for y'all. If you ever wondered in your life, why the heck imaginary numbers, what's up with those? They actually have connections to the real world, and they're useful for things, as weird as that sounds. Just trust me that they actually have physical use. So that's kind of cool. That thing that you learned, who knows when you learned about imaginary numbers? I have no idea. I think the answer is 0.7 something, just from my memory of this morning doing it. 0.755 maybe. Again, that's not me doing the problem in my head. That's me trying to remember what the answer was from doing it this morning. Nowhere close. Told you all my memory's terrible. All right, that gets rid of the squared. Doing the square root gets rid of the squared. All right, and that's my answer. And we should always ask ourselves, is that reasonable? You all have seen lots of things fall in your lifetime. You have likely been one of those things that fell. How safe is this? This is sturdy enough. All right, so 3 meters up. I think in this room the ceiling is, no. All right, this isn't quite 3 meters. Maybe like, I don't know. This is close enough. I will drop an object from 3 meters and we'll time it. 1, somewhere around 1 second. You could time it on a stopwatch if you wanted to. But it took about a second. It does not take that long for things to fall. And the next problem is to actually show us that when things fall, there's a reason this time is pretty short. Things get going fast really quickly. It does not take much time for things to reach a really fast velocity. This is why if you jump off a second-story building or a third-story building, you'll break your legs when you hit the bottom. Unless you know how to land right and all that jazz. You get going really fast, really quickly. Gravity might not feel like that much because you're used to it and you're walking around and you're like, yeah, I can walk around and all that stuff. But at the same time, hopefully you're scared to jump off a third-story building because even though you only fall for like 1.5 seconds, maybe 2 seconds, you're going to hit that ground going real fast. And that's just from like 2 seconds of gravity. It's like nothing. Anywho. Not that. Oh, I haven't added that. I thought I copied these. No, I didn't copy these ones. All right. So I'm going to make the problem here just to prove a point, and we'll do the calculation. So reminder to you all, the benchmark that we use in this class for velocity, the one that I find very useful, is 27 meters per second. So remember, 27 meters per second is roughly 60 miles per hour. Like that's the nice little touchstone. So how long does something have to fall starting at rest? Let's put that at the beginning. An object starts at rest. How long does it need to fall to reach 27 meters per second, i.e. 60 miles per hour? Pretty darn quick. If you're going 60 miles per hour and you hit something, it ain't going to go well for you. You yourself as a body. If you jump off something and reach this velocity. So, we're going to solve this the same way we solve all of them. What's given, what's missing. And you're going to find this really common in these like problems with gravity. I only have to give you generally like a single number. The rest is all tucked away in there somewhere. So, object starts at rest. V initial is 0. V final is 27. My acceleration in the y direction is negative 9.8 meters per second squared. And that's all we got so far. If you really want, you could pick the initial position to be 0. You can pick the initial position to be whatever you want if it's not stated, but we don't need to here. Step 2, what are we solving for? How long does it take? Step 3, we choose the equation. I'll let you all hunt that down. I'm going to copy and paste it over. See if y'all can find the right equation. Honestly, writing the givens and the missing is, in my opinion, the trickier part. Choosing the equations nice and straightforward, but I already kind of jumped ahead on that. All right, again, there's several pathways you can take. There's one pathway that's just one equation and you're done, but you could also like find the distance you travel and then do an extra step, and there's nothing wrong with that. But I'm going to opt for this equation right here. It's a one and done situation. So VF equals V naught plus AT. Straightforward, plug and chug. Ooh, I made a mistake here. See if you can spot it. It's in my givens. I'll give you all, this is always a good opportunity. One of my givens is very slight, I say very slightly off. It's a tiny little change we're going to make that has a drastically different representation, what it means physically. So I'll give you all 20 seconds. See if you can spot my mistake in my givens. And then, yeah. So hold on. Don't say anything else. Don't spoil the surprise. People are trying to figure it out. All right. Anyone spot it? Yeah. It should be negative. Which way do things fall? Down. I currently said my thing's flying upwards in the air. It's nonsense. Now, again, a good question here. How did I find that out? When I was doing this step, how did I realize that? Because it's always good to realize how do you identify mistakes. I realized if I put in these numbers, let's just plug in these numbers and see what happens. So we can kind of spot the mistake together. So 27, again, this is not, there's a mistake here, and we're going to see it. It's a tiny little mistake, but if we do this math, 27 divided by negative 9.8, you get a negative time. That means I went backwards in time. We're never going backwards in time. It's not happening. Technically, the physics equations let you do it, which is why people think about time. All the equations I'm giving you work with negative time. They have no problem with it, which is why people think about time travel and all that stuff. But in our class, no going backwards in time. So this should be negative, and in this case, it wasn't a big deal. In other problems, it can actually result in you having an answer that's completely wrong. It can result in not just your answer having the wrong sign, but actually in a completely wrong number. An easy example of that is this equation here. Y final equals Y initial plus V initial t plus 1/2 AT squared. If you're adding the wrong sign, it's going to completely change your answer. So just one of those things to watch out for. Anytime I make a mistake, it's always a good opportunity to point out that every single step here is an opportunity to make a mistake. All right, so the negatives cancel, so life is good. We're not going backwards in time. Negative 27 divided by negative 9.8. And this number actually worked out pretty nice. 27 is divisible by 9. This is close to 9. Our answer is going to be close to 3 seconds. It's going to be a little bit less, but it's pretty close, which is nice. So 2.76 seconds. You only, assuming no air resistance, you only need to fall for about 3 seconds to reach 60 miles per hour. Not much time. Like 1, 2, 3. Now I say that, you can imagine someone falling if you counted that out. If you know this, you see that. If you see anyone falling and you can count, it's not going to go well for them. You know that, but it's connecting it to the numbers, again, connecting that knowledge. If something's falling for a large time, it's going to go a really big distance, and it's going to be going really fast when it hits whatever it hits. So it's just good to remember that. This is also a good point that, remember, what does acceleration mean? It means every second, that's how much my velocity changes. After 1 second, how fast am I going? Negative 9.8 meters per second. That's literally all this equation's doing. It's just taking the acceleration and multiplying it by time. After 1 second, I'm going negative 9.8 meters per second. After 2 seconds, I'm going negative 9.8 times 2 seconds. Oh, did it do the thing? Fingers crossed. Okay. I used to have ghosts that appear. Anyway, after 3 seconds, I'm going negative 9.8 times 3. That's literally all this equation is doing. Take the acceleration, multiply it by time, add it up. This is a helpful exercise to remind you all what the heck acceleration is. It's how much your velocity changes every second. Every second, it's changing by this amount. Take whatever your velocity is and add that number to it. After another second, add that number again. After another second, add that number again. Anywho. This also gives you, when we could say G's, how many G's something experiences, that's how many multiples of this value. 2 G's, 2 times negative 9.8. 3 G's, 3 times negative 9.8, so on and so forth. All right, last few concepts, and then we'll do a problem, and then we'll jump to 2D. These last problems, I'm going to straight up, these are very important problems to help solve these problems. And yeah, some of these are going to throw people off, and that's okay. That's the reason I'm asking them. If I toss an object upwards, like my baseball, I'm going to model this for you all. I toss it upwards at 3 meters per second. That's about 6 miles per hour if you do the conversion, roughly. What is its velocity at its highest point? So I'm tossing this baseball at its highest point. What's its velocity? Just keep tossing it so you have the reference. And we're tossing it straight upwards. Or I can even say, what's its y velocity at its highest point? For now, straight upwards. Is it 3 meters per second? Negative 9.8 meters per second squared, 0 meters per second, or negative 3 meters per second. There's only one right answer. Oh, if you're doing math, you're doing it wrong too. All right, we'll go like 10 more seconds. All right, in 5, 4, 3, 2, 1. So to answer this question, we're going to break it into pieces. All right, at some point my ball is going upwards. Is its velocity positive, negative, or 0? Positive. Fantastic. On the way up, its velocity is positive. What about on the way down? Negative. The only way you can go from a positive number to a negative number is you got to pass through 0. You have to. If you draw a graph of velocity versus time, if your velocity is positive at some point, it's negative at some point, you got to connect those lines. At some point, you pass through 0. At the highest point, it's 0 because it has to stop to turn around. So this is super important. I won't tell you, I'm not going to tell you this in a problem. This is one of those things that in a problem I might say, how long does it take to reach the highest point? And this is a given. At the highest point, its velocity is 0. V final equals 0. So that's one of those like things that comes from, you all have seen lots of things go up and down. And something I'm also going to put here, Vy. So I'm going to put this notation because when we get to 2D kinematics, in the vertical direction, the velocity is 0. If something's going horizontally, it is still going to be moving horizontally at the highest point. So we'll see that with 2D. But for now, just foreshadowing. But the y velocity is definitely 0. It stops, and then it comes back down. All right. Let's see how we did there. Pretty solid. Okay, and never be bothered if you miss any of these. The purpose of these is I don't expect you all to get all these right. If I toss an object upwards with a velocity of 3 meters per second, what is its acceleration at its highest point? Again, chat with the people around you. See what they think. There's only one right answer. Again, if you're doing math, you're doing it wrong. All right, 10 more seconds. And 5, 4, 3, 2, 1. All right. This is also a fun one because test taking skills, there's only one answer that's possibly correct, even if you knew nothing else. If you know your units, only one of these has units for acceleration. So that's going to be the answer. But, so the answer is negative 9.8. Acceleration isn't velocity. Acceleration is how much is my velocity changing every second. At the highest point, it is experiencing gravity. Gravity is going to make it float on. If there wasn't an acceleration at the highest point, it's going to stay there forever. Its velocity is 0 at the highest point. If there's no acceleration, why should it get faster or slower in any direction? In space, if you get far enough away from the Earth, there is no acceleration. So yes, if I place something somewhere, it stays there forever. If I toss something, it'll go forever. But in this case, it's going to come back down. Because gravity, at every single point in its trajectory, A is negative 9.8. On the way up, A is negative 9.8. At the highest point, A is negative 9.8. On the way down, A is negative 9.8. At every single spot, A is going to be negative 9.8. Sure, my velocity is positive. Sure, my velocity at the highest point is 0. But the acceleration is the same everywhere. Everywhere. That's what lets us do these problems. It's a constant acceleration. Always. This is why we can write it as a given. I am not going to give you all problems where the acceleration is changing. You can't actually use the kinematics equations if the acceleration is changing. So that's just a fun fact there. But yeah, this is a key point. This is a classic trap people fall into of mixing up acceleration and velocity. Just because something isn't moving at some specific time doesn't mean it's not accelerating. Sounds weird, but the rationale is right before this it was moving, right after this it's also moving. Its velocity is changing. It's not stuck there. So it's a classic, and it's just one of those. I ask these questions because they're really important to remember. All right. At all times, G is negative 9.8 meters per second, and the unit here is wrong. I fixed it this morning and forgot to fix it here. Boom. And also, I want to remind you all that this G is going to equal your acceleration in the Y direction. If something is in the air, I don't care if it's moving left, right, up, down. If gravity is the only thing affecting it, no air resistance, no rockets, no propellers, no anything pushing it, A is negative 9.8 in the vertical direction. And it slows down on the way up, it stops at the top, and it speeds up on the way down. So on the way up, V is going to be a positive number. At the top, V is going to be 0. And then on the way down, V is going to be negative, like matches your expectations. So that's an important thing just to keep in mind. Positive, negative, all that good stuff. All right. So gravity. It's fun. It's all around us. Helps us understand a lot of things that go through the air. And a lot of things go through the air. Okay, so there's another 2 slides on like things that are helpful to know about an object going up and down. So many things. I toss a ball upwards. How does the time to the top, so the time from the lowest point to the highest point, how does that compare from the highest point back down to the lowest point? So it's returning. I'll even draw a picture of this for you all. So the ball starts somewhere, and then it reaches the top, and some time passes. How does that time 1, compare to the time it takes to reach back down to where it started? It goes up, and it goes down. How do these 2 times compare? The time to reach the highest point, and I had to kind of draw them left, right, otherwise I have to draw them on top of each other. So if I toss this baseball up, how does the time from my hand to the highest point compare from the time from the highest point back down to my hand? Are they the same time? Is time 1 greater than time 2? Is time 1 less than time 2? Or who knows? Not enough information. As always, assume no air resistance. You only have air resistance if I say it's in the problem. Like that's the running thing. The running assumption is no air resistance unless I say otherwise. All right, we'll go 10 more seconds. And we'll close it out in 5, 4, 3, 2, 1. All right, so this one's a little bit tricky to prove without the next question. So I'll actually come back. I'll prove this one after the next question. But the answer is it's the same. And so if you just watch me tossing this ball upwards, it's a symmetrical problem. On the way up and the way down, if you actually like recorded this and played it in reverse, you wouldn't be able to tell the difference other than my hand would look a little weird. A ball going up and a ball going down, like it's the same motion on the way up. It's the exact opposite of on the way down. And that's a really important, it's a very symmetric, because the acceleration is the same the entire time. The acceleration is the exact same the entire time. The distance it travels is also the exact same the entire time. So there's symmetry to it. They're basically the same problem but backwards. So I'll do the next one. And then the next one is easier to prove with one equation. And then after I prove this, the next one, I can come back and prove this one. One day I'll switch the order of these. All right, I toss the ball upwards with a velocity of 10 meters per second. It's pretty fast. That's about 20 miles per hour. But people can throw a ball that fast. That's not hard to do. What's the velocity when it returns back to my hand? Is it 5 meters per second, negative 9.8 meters per second, 10 meters per second, or negative 10? So use the information from the last problem. Use the symmetry. All right, give you all 10 more seconds or so. Again, no math, just thinking through. In 5, 4, 3, 2, 1. All right, so it's because it's a symmetrical problem. However fast it leaves my hand is exactly how fast it's going to be when it hits my hand, but it's going down. If you say it's positive, that means it's going up. Again, doesn't quite make sense. So nice work. And then this one I can actually prove. It's just from the equation. So VF squared equals V naught squared plus 2A change in Y. So that's just one of our equations. If my initial velocity is 10 squared, I know my final velocity. Remember at the highest point it's 0. So I can calculate how far it traveled from this equation. I can figure out the height of it. Nice and straightforward. Can do the math. I'll leave it for you to do the math, but it's going to be 100 divided by 2 times 9.8. You know what? I'll write that down here. And the negatives will cancel, so that's good for us. So this is just telling us how high it goes. There's another negative. I already have the negative. Oop. Negatives will cancel. I know I put them in awkward places, but it still shows the thing. All right, so how high is this thing going to go? 5 meters. 5.1 meters. Great. If it goes up by 5.1 meters, So, it's traveling. It's going to go 5.1 meters. It's also going to fall 5.1 meters. However much it goes up, that is how much it goes down. Exact same. So if I just redo this equation, so that was my on the way up. On the way down, we're solving for final velocity. No idea what it is. Let's find out. Our initial velocity is 0 because we're at the highest point. 2 times negative 9.8 times my delta y here is going to be a negative because we're going downwards. You do the math. 2 times negative 9.8 times negative 5.1. You're going to get that VF squared equals, and this is going to, due to rounding, it's going to be 99.96. That's because we rounded. It's 100. If you use the actual velocity here, the actual distance, it was 5.10204. If I put that whole number actually in my calculator, this would spit out 100. And this is actually a good exercise for us to do because I want to point out something. VF, what's the opposite of squared? Square root. Fantastic. So you might look at this and say, but the square root of 100 is 10. Correct. Plus or minus 10. This is something that sometimes people fall into the trap of. They do the square root and they always take the positive. Negative 10 squared is 100. Positive 10 squared is 100. You have to make a judgment call. And in this case, we know it's going down. How do you make the judgment call? When a thing returns to my hand, which way is it moving? Down. So it's negative 10. If you say it returns to your hand with positive 10, you're saying it returns to your hand traveling upwards, which is really hard to visualize. And I can't even describe what that would look like because it just doesn't make sense. Yay, we've proved the answer. And if you know this, then you can go back to this one and you can do VF equals V naught plus AT, and you can have so much fun and prove it for yourself that this is true. That's for your own enjoyment. I'm not going to do it. But you know their final velocity on the way up. You know that the initial, so on the way up, the final velocity is 0. The initial velocity is 10. Do the math and find time. On the way down, you know the final velocity is negative 10. You know the initial velocity is 0. Do the math. You'll find the time is exactly the same. That's great. So there you go. Proof. Yay. Or just take a video of something and play it in reverse and it looks the same. And I think that's more fun. All right. What's the consequence of this? One of the interesting ones is you probably heard like well, maybe you haven't. I don't know. It's a weird thing. Don't fire guns in the air, like during 4th of July and things like that. Why? They'll return to the ground as fast as they left the gun, assuming no air resistance. That's pretty fast. Like, that's dangerous because it's a bullet. And, you were standing in front of the gun when it left. That's as dangerous as when it comes back down. So yeah, if you fire bullets straight up in the air, they're going to come back down. Maybe not as fast because they're going the air will slow them down, but pretty darn fast. Like, I'd have to look into it in terms of how dangerous it is, but probably pretty dangerous. A bullet's pretty small. Like, air is not going to affect it. They are made to not be affected by air that much. Like, that's in their design. So yeah, anywho, I don't know. So that's like an obvious thing. Probably don't shoot guns into the air, but this is why. Now you know the physics. How exciting. It's one of those, it's a cool use case of it. But there you go. All right. It also, you all know this. If you toss something really high, it comes back and it hits your hand just as hard. Hurts. Whatever. Okay. This one is just practicing this. I'm just going to do like one of these because once I do one of them, they're all the same. So they're good practice for you. Calculate the displacement and velocity at the following times for a ball thrown straight up with an initial velocity of 15 meters per second. Take the point of release to be y equals 0. You all do the givens. I'll give you all a chance to try it. I've been doing it up to this point. There are... How many givens? 1, 2, 3, 4 givens. Yeah, 4 givens. All right, so y'all tell me what's given. Initial velocity is, sorry, what was it going to be? 15. Nice. What else? 3 more. Yeah, I started 0. Fun, and I didn't put the unit here. What a chump thing for me to do. Unless otherwise stated, you can make 0 anywhere. In this case, they said 0 is where we start, but you all can make, remember, reference. You can choose whatever to reference off of. In this case, it's given though. 2 more. Acceleration is negative 9.8. It will not tell you that in the problem. It is a given on your formula sheet, but it's one of those things you have to realize. All right, one more. The time. 0.5 seconds. We make our nice little list of givens. One of our goals when doing step 1 and step 2 is if we get everything down, we don't have to read the problem anymore. It's very nice. We're translating. All right, what are we solving for, y'all? Final velocity. Good. That's one of the things. And then what's the other thing we're solving for? Displacement, which is going to be delta y. Now, this problem is quite convenient. So remember, delta y is yf minus y naught. Well, if y naught is 0, we can also just say we're solving for yf. It's the same. If y naught is 0, then that's all it is. So that's kind of nice. And this is where, in problems, you generally want to choose either your starting location or your ending location is 0. Because then it just makes one of the values 0. The more things you can make 0, the easier the math is. 0 is the best number to plug into an equation. Adding 0, you get rid of it. Multiplying by 0, you get rid of it. It's great. Fantastic. 10 out of 10. All right. Choosing the equation. So again, you go through the list. You choose them. So many options here. I'm going to do the velocity one first because it's actually super easy. VF equals V naught plus AT. How did I choose it? Oh, it has what I want. And it has what I have. That's all you do when making the decisions. The position one, this one's always like the bread and butter one. YF equals Y initial plus V initial T plus 1/2 AT squared. Let's double check that. I always look at the list. So like I'm doing this off the top of my head and I'm still going to double check myself because, but I look at the list even when I do these. Like I write them all out. It's just easier to see them than to have them all in your head and run through. I'm solving for YF. I have V initial. I have time. I have A. I have T squared. Yay, I can do it. That's the thought process, y'all. All right, and step 4, do it. So this is the easiest step. Step 4 should be the easiest one because it's just putting numbers in. Step 4 is actually not physics. It's just math. Steps 1, 2, and 3 are the physics. Step 4 is just, can you plug things into do algebra and plug things into a calculator, which I wouldn't necessarily call physics. But that's fine. It gets us an answer. That's interesting. As a physics major, eventually you just stop using numbers and you work purely in variables. And so like step 3 would be our final answer and we'd be done. As a physics major, we just leave things in terms of variables. But we're not physics majors. I got to teach you all how to plug things in. So here we go. So you just add those together. It gets us a number 15 plus negative 9.8 times 0.5. And we got 10.1 meters per second. So a little bit after it leaves, it's still moving upwards. Makes sense. Great. Let's do the second one now. Y final equals, so Y final is what we're solving for, equals Y initial plus 15 times 0.5 plus 1/2 times negative 9.8 times 0.5. Ugh, just quite didn't fit. And that's just a nice plug and chug. Stick that whole thing in your calculator. I'm going to move everything up so I don't have to make a new slide. So really the skills I'm teaching you all are steps 1, 2, and 3. And then step 4 is just practicing skills that you've hopefully gotten some experience with in the past. If not, that's fine. You're going to get lots of practice with it in this class. You're going to plug lots of things in equations, but shouldn't be anything too new. And this is where I remind you all, having a calculator that lets you see what you're typing is best. Because you could get to step 3 and do it all perfectly. And if you fat finger the wrong number, you get the wrong answer. And that's really hard to diagnose when you can't see what you typed. If you have a calculator that when you hit enter, it disappears everything you just typed, troubleshooting that's really hard. Having good documentation is like just a good thing in life in general. And a calculator that lets you see what you're typing is effectively documentation. Anyhow, that's my little soapbox. And don't forget your units, all that good stuff. It is worth spending all the $15 to $20 on a scientific calculator that has 2 lines on it. Like, they're not super expensive. You don't need a graphing calculator, but I will tell you this graphing calculator is from when I was in high school. These things last forever. Like, all I've had to do is change the batteries. So high school for me, just to age myself, I've had this calculator for 15 years. Still going strong. Longer than a lot of kids have been alive. Anyway, there you go. That's 1D motion. All right, we're going to start into 2D just so I can make one point that's going to show up on like a bunch of slides and it's all caps, bolded. 2D kinematics is not, it's not really any new skills. There's one new skill in 2D kinematics. There is no new equations in 2D kinematics. It's all the equations we've been using so far. So I'm going to jump over to it, go through what we're going to talk about, go through the most important new skill, and then we'll kind of leave it there. I'm not going to be trying to jump through a bunch of things. All right. Behold, as I have made the most important new skill, like giant, recognizing that x and y are independent of each other. Remember vectors, x and y, we cannot just add x and y components. X and y are independent of each other. What 2D kinematics is just doing 1D kinematics problems twice. In the x direction and in the y, x direction and the y direction. So the kinematics equations, we're just going to do them twice. Once horizontally and once vertically, using the skills that we talked about. All the things we just did with gravity, you're going to use that for the vertical direction. The horizontal direction is actually really, really easy. It's a constant velocity. We'll see that in a bit. But for now, this is the skill. This is the only new skill in this entire PowerPoint. Everything else is just taking what you learned and putting it together. That's all this entire PowerPoint is, in fact, hey, what do you need to remember? All the things we've been over so far. Vectors, how to break things into x and y, drawing right triangles, all that goodness. The definitions, just useful to remember. It's not the worst thing if you forget it. 1D kinematic equations, because we're just going to use the same equations just twice. And then gravity in the y direction. Acceleration is negative 9.8. And that's basically all we're going to be like. So we're going to just be using these. X, y independent. X and y are independent of each other. You should never have an equation where I have an x component and a y component together. You should never have a kinematics equation. So let's say you have this equation. X of t equals x naught plus b naught t plus 1/2 at squared. I should never put a y component of acceleration with an x component. X's and y's are separate. That's bad. No x and y's together. All y's or all x's never together. There's only one equation where x's and y's go together. And that's when you're combining them with Pythagorean's theorem. That's the only time you all can combine x and y's is Pythagorean's theorem. If you say, hey, I want to figure out how far I went. Pythagorean's theorem. 2 sides of a triangle. This is the only way to combine x and y's is Pythagorean's theorem. The only way. So anyway, I mention this because this is a common mistake. People will take x variables and put it with y and vice versa. So the more I can hammer it into your heads, the better. So do I want to spend the time on it? You know what? I'm actually going to jump way down. We're going to do 2 last little clicker questions and we're going to call that good. I'm going to skip through all these slides because they look more intimidating than they're worth. I will come back to them and we'll do them and it'll be so much fun. But just to prepare us for projectile motion, I think one of the most helpful things is these 2 slides. These get the idea across. All right, where's my baseball? I got some object. I don't have demo deck with me, but I always have a baseball in my pocket. Great. I chuck it across the room. Hiya. Didn't break the wall. It's fine. What is my acceleration in the y direction when it's in the air? So after that baseball left my hand, in the up-down direction, what is my acceleration? Nice. As it's flying through the air, how much is it speeding up / slowing down in the up-down direction? Is it 0, positive 9.8 meters per second squared, or negative 9.8 meters per second squared, or non-information? Assume no air resistance. I know it says air in this problem. Assume no air resistance. I had to say something about after it left my hand. While it's flying through the air that we're ignoring. It's really hard to describe something being in the air without the word air. It's just a fun challenge. All right, 10 seconds. 5, 4, 3, 2, 1. Boop. So this is just what we spent the entire time talking about. In the y direction, it's negative 9.8 meters per second squared. Always. Don't care where it is in the flight. Don't care on the way up. Don't care it's moving to the right. Don't care. All I care about is it's in the air. There's no air resistance. There's no rocket attached to this. After it left my hand, gravity's pulling it down. That's happening. So, boom, negative 9.8. Fantastic. All right. Had so much fun the first time. I do the exact same thing. I chuck something across the room. Hiya. What's its acceleration in the x direction after it's left my hand? So same thing. While it's in the air, same exact question. Now I care about the left-right. Before we cared about the up-down. Now I care about the left-right. No math required here. Just thinking through the logic. What does the word acceleration mean? All right, we'll go like 10 more seconds. 5, 4, 3, 2, 1. So the key to this is anything making it speed up left, right. As it's going through the air, is anything pushing it left or right? No. So the acceleration in the x direction is 0. Nothing is making it go faster left or right at all. And if you want to prove this for yourself, me tossing a baseball like this, if I was inside a bus going 60 miles per hour, nothing changes. If I'm going in a bus 60 miles per hour and I toss this baseball, you can't tell the difference whether or not the bus is going 60 miles per hour or 0 miles per hour. So me tossing this baseball like this, if you all saw me standing in a bus and I was doing this, it wouldn't look any different. Even though it's traveling 60 miles per hour to the right, that bus is moving. So technically this thing's moving 60 miles per the right. If you were outside the bus, and you actually just look at the baseball, you would see it make an arc. Even if you were on the bus, it would be going up and down. Whatever. Doesn't matter whether or not it's moving left to right. It still does the same thing. Still does the exact same thing. And this is one of those things to realize that gravity only affects things up, down. Left, right, it doesn't matter. And this is one of the things that's going to throw us off in these. And I'll try to give more examples of this. But yeah, prove it for yourself. When you're driving a car at a constant velocity, tossing something up, it's just going to return right back to your hand. Even though your car is going however fast you're going. As long as you're not hitting the gas. Even then, it won't really matter. But, well, go behind you. Anyway, That's good enough for today. The last thing I guess I want to show you, to solve these problems, we're going to make a big table with like initial velocity, final velocity, acceleration, initial position. We're going to split them up and make a big old table of givens for every problem. We'll see that when we start solving them. Foreshadowing. X and Y are independent. That's the main theme.